So before I start, let me just say, so this is the last lecture. Tomorrow morning there will be another problem session. Hopefully you didn't solve all the problems yesterday. I might add a few more from today's lecture, but that's the plan. Let me just pull this up here. Okay, so we're nearing the end of the construction of exotic negatively curved manifolds. So let me restate the main theorem that we're proving. Right, so this is slightly weaker than the statement I made at the very beginning of the first lecture, but I'll explain that. So let's fix an exotic n-sphere, sigma. Then for any closed hyperbolic manifold M, there exists a finite cover such that M hat connects some sigma has a pinched negatively curved metric and is not diffeomorphic to M. Okay, this is a bit weaker than what I said last time, or at the beginning, because this produces examples in all dimensions where there's an exotic n-sphere, which is not all dimensions. So we can almost prove this. We need one more fact, which will be sort of the main thing we'll discuss today. I'm going to call this theorem A. Oops. And so M is closed hyperbolic. And so let me just say M and sigma as above. So then if M connects some sigma is diffeomorphic to M, then they are concordant. Okay, so let me remind you about concordance, and then I'll explain why with theorem A we can finish the proof of this, and then we'll discuss the proof of theorem A. So, right, so recall two smooth structures. M0 and M1 on M. These are concordant if there exists a smooth structure on M times the interval such that at the endpoints, m times I this is MI. Yeah, so let me just say this. Let me say it slightly. It's going to be important to be a little more precise about this. So whose restriction to M times I is MI. Okay. And the picture is like this. And it's helpful to remember, so there's a theorem that says concordance implies diffeomorphic. So things that are concordant are in particular diffeomorphic, at least if n is at least 5. Okay. So stop me if there are any questions. But next, let's prove the main theorem. We've already done most of the work. So choose M hat such that M hat has a point with large injectivity radius. So this will guarantee the curvature condition. By the warping method, which we saw last time. And we also want, or we can choose the cover so that M hat is stably parallelizable. Thanks to Deline and Sullivan. Did anyone solve the challenge from last time? I can also put your name here. Okay. But that implies then that M hat connect some sigma is not concordant to M. I gave a proof of this fact last time. This was the argument involving Whitney embedding. And then, right, and this is where we use stably parallelizable. And then theorem A, so theorem A then tells us that these two are not diffeomorphic. Yeah, so theorem A not concordant tells you not diffeomorphic. Okay, questions about that? Yes. Oh, yeah. Yeah. Thank you. Yes. Thank you. Yes? Yeah, so I'm going to discuss some variations. Yeah, so yeah, I'll comment on that. It's a good question. The short answer is no. but I'll say a bit more in a bit. Okay, so so it remains to prove theorem A. And you might worry that this is going to be some more complicated, high-dimensional manifold topology thing. But at the end of the day, we're going to see that this follows from some rigidity facts. So Mostow rigidity and the Borel conjecture will deduce this fact. But before we get there, I want to say a bit more about concordance versus diffeomorphism. Yeah.
You already explained personification.
This one here, or this one here. Yeah, this was last time. Towards the end, the argument with Whitney embedding. Yeah. And smoothing theory. I guess the short thing is that this is using smoothing theory. Okay, I think it's easy to be a little bit confused about this notion of concordance and how it relates to diffeomorphism. So here's an incorrect argument that concordance implies diffeo. So suppose M, or no, sorry. No, that's the thing that holds in general. I meant to write the other way. Okay. Diffeo implies concordance. So you might think, okay, I have M naught, which is diffeomorphic to M1. I want to construct a concordance. So then M naught times the interval has an obvious smooth structure with M naught times 0 is M naught, and M naught times 1 is diffeomorphic to M1. So on the boundary, you see M naught and M1, and that's a proof they're concordant. Okay, this is an incorrect argument. And the key thing is to properly understand what is means here. And so let me explain that now. Okay, so so to be more precise, so so the way to see what's going on is as follows. So an element of this structure set, so remember this was smooth structures on M up to concordance. It is represented by a marking, which I'll write as a pair x comma f, where x is a smooth manifold and f is a map from x to M, which is a homeomorphism. Okay, so given a marking, you get a smooth structure just by taking a smooth atlas and pushing it forward. Okay. Right. So the next thing is two markings. Say x naught f naught x1 f1 determine the same smoothing if and only if there exists a diffeomorphism between them, say like this, so that this diagram commutes. Okay, this is like an exercise. And then in terms of concordance, so two markings are concordant. This can be phrased in terms of markings. So if there exists YG, which is a smooth marking, which is a marking of m times the interval with, so the boundary of y is diffeomorphic to x0 union x1, the two things that are concordant. And G restricted to xi, which is a map from xi to m times I. This is determines the same smoothing as fi for I equals 0 and 1. Okay, these are the definitions. Let me give you an example which hopefully will make things clear. Okay, so let's take M to be a product of spheres. And let me give you two smoothings. So one okay, so the manifold is going to be exotic sphere times standard sphere. And I need to also tell you the map. So remember, an exotic sphere comes with sort of a standard homeomorphism, which is like coning, or this is coming from the Alexander trick. And so here I'll do C times the identity, or the identity times C. Okay, and now let's think about whether these two smooth structures are determine the same smoothing, concordant smoothings, or if they're diffeomorphic. So first of all, these do not determine the same smoothing because, well, you need the composition, so this is commutes, you need this composition to be a diffeomorphism. And, well, the composition is C times C inverse, or C inverse times C, whatever. And this is not from sigma times Sn to Sn times sigma. It is not a diffeom. They're also not concordant. And well, you could prove this formally. Let me draw a picture to try to convince you of that. So let's see. Okay, so this is a picture of Sn times Sn. And in one, you change the smooth structure on the meridian. And in the other, you change the smooth structure on the longitude. And the question of whether they're concordant is whether you could put a smooth structure that interpolates between these two. But there's no obvious way to do that. I mean, and yeah, I mean, in fact, you can check with the smoothing theory computation, and I think this is in the exercises in a way, that these two smoothings are not concordant. And then so they're not concordant, even though they are obviously diffeomorphic. Okay, so the short summary is that in the definition of concordance, these are smooth structures on M, and M is like a fixed manifold, is a fixed topological manifold, and the way M wears the smooth structure is important, and concordance can sometimes detect that. But diffeomorphism does not. Okay. Questions?
Can you say a bit more why the Sn is represented by these markings?
Yeah, well, so so there's not much to this. I mean, if you have a smooth structure on M, yeah, it's almost tautological. I mean, if you have a smooth atlas on M, then that gives you a marking just via the identity map. But it's helpful to think of these markings as possibly something slightly more general than just M. You have some other smooth manifold and a map to M, which gives you the marking. Other questions? Yes?
Doesn't the fact that, maybe I'm confused, but the fact that these are not concordant, doesn't it follow from the first bullet point? Or
Well, determining this is a stronger condition that I mean, in general, concordance is more flexible than determining the same smooth atlas on M. Maybe I misunderstand the question. Is that? Okay. All right. Let me mention in passing one more example. So similar to this. For M hyperbolic, the smoothings so one way to change the smooth structure is, instead of removing a disk and gluing it back, you could remove a solid torus. And maybe this is a thickening of a geodesic. And then you can glue. There's various gluings you might think of, but one option is just to glue in this way by a diffeomorphism of Sn minus 2. So these smoothings depend on two parameters, the homotopy class of the curve you remove, and then the gluing map here, gamma and phi. And for these, it's possible these can be concordant, but not diffeomorphic. Diffeomorphic but not concordant. So this is something that is explained in a paper of Mauricio and I. I mean, it's similar to this, but it's a bit harder to show. And so this is relevant for the discussion of theorem A. So just note that theorem A says this doesn't happen for M connects some sigma and M. Okay, so like theorem A is not just a general statement that for a hyperbolic manifold, whenever you have two different diffeomorphic smoothings, they're concordant by this type of statement. But for these particular types of smoothings, M connects some sigma, you do have that conclusion, that diffeo implies concordance. Okay. So now I'd like to move on to discussing the proof of theorem A and the ingredients. Any questions before we do that?
Aren't they always diffeomorphic?
I think not always. So one way to get that these would be diffeomorphic is if, say, the two geodesics, you take two of these, and the geodesics differ by an isometry of M. Then Right. Okay. Okay, so this is ingredients for theorem A. And these are, like I said before, the ingredients are rigidity results. So the first is Mostow rigidity. Which, so here N and M are closed. Well, they could be finite volume, but for us, closed hyperbolic manifolds. Then every homotopy equivalence from N to M is homotopic to an isometry. And we'll use a particular corollary of this, which says that well, yeah, so that's saying that, so there's a map from the isometry group of M to homotopy automorphism of M, which is the same on pi 0 as outer automorphisms of pi 1. I guess I have to write pi 0 here. Or, no, just let me put a map. There's a map like that, and it's a homotopy equivalence. This map is surjective. Okay, so, right. Any homotopy, the theorem says any homotopy equivalence is induced by an isometry for M, if you just apply it to N equals M. And then, you could equivalently think about this as just automorphisms of pi 1. Okay, and then the next form of rigidity we'll use is Borel rigidity. So this statement is due to Farrell and Jones. And it says, so now M is closed hyperbolic, but N now will be a topological manifold, not assumed to be hyperbolic. And I should say here N at least 3, and in this statement N should be at least 5. So then any homotopy equivalence from N to M is again, is homotopic to a homeomorphism. Yeah. Yeah, right. If I say this squiggle means homotopy equivalence, then I think it's okay. But yeah, let's just say up to homotopy, and then yeah, I agree. Yep. So the statement we'll use is actually a relative version. So let me write of Borel rigidity, which is that if if you have n times the interval mapping to m times the interval, and this is a homotopy equivalence and a homeo on the boundary, then, sorry, I'm running out of room, then it's homotopic rel boundary to a homeo. Okay. Okay, so these theorems are two big hammers, and with those, the proof of theorem A turns out to be quite easy. So let's do that. Let's see that. And then I think maybe we will take a break after this. Okay, so we're given that we have a diffeomorphism from M connects some sigma to M. And let me denote by C the map between them, which is a homeomorphism, the coning homeo, which is the Alexander trick again. Okay, so now the first observation is, okay, the first we'll use Mostow. So okay, so we have this composition. We would like to make this induced map on pi 1 to be homotopic to the identity. Okay, it might not be at the beginning, or this composition need not be homotopic to the identity, but it induces some outer automorphism, and up to changing by an isometry, we can arrange for it to induce the trivial map on pi 1. So there exists alpha an isometry of M such that if we compose further with alpha, this induces the identity on pi 1, hence is homotopic to the identity. Okay, and let's write the homotopy as a map like this. Okay, so we have this, so H, yeah, so yeah. So I have like H on M times 0 is the identity, say, and H restricted to M times 1 is this composition, alpha F C inverse. Okay, next we apply Borel, the theorem of Farrell and Jones, to replace, so H this H is a homotopy. It's just a continuous map, but we at least know on the boundary it's a homeomorphism. So H is homotopic rel boundary to a homeo. Okay, ultimately we need to construct a concordance, and let's do that now. So the concordance so we're almost done now. So now what one can do is consider the following composition. So So this composition defines a smoothing on M times I. This is a marking for a smoothing. And the claim is that this gives a concordance. Okay, so let me just say, so check. Let's write that here. So check. And this is an exercise that this marking defines a concordance between M and M connects some sigma. Okay, all you have to do is just look at the map on the two boundary components and identify which smoothing it determines, and you see that these are the two. Okay, so that's the proof of theorem A. The main, as you see, the main ingredients are just these rigidity, and then you can deduce it quickly. And given that, we've now finished the proof of the main theorem. So after the break, I'll discuss some variations of this. In particular, at the beginning, I claimed that a similar statement holds for every n at least 6, and I'll say something about that. And then, I'll finish with some additional remarks. Are there any questions before the break? Okay, so why don't we take a 15, I guess maybe 16-minute break and come back at 35? Okay, so so let me tell you about some work that's been done since Farrell and Jones proved this theorem, a couple of points of interest. So the ideas we discussed so far have a lot of mileage. One thing, so you can get examples of exotic negatively curved manifolds in dimensions at least 6 by changing the PL structure right, so I don't want to go into this too much, but you think intuitively, well, smooth manifolds a smoothing determines a PL structure. Like if you have a smoothing, then you get a triangulation, and that is like a PL structure. Yeah, I mean, on a topological manifold, you can have multiple PL structures. So that is reflected by, this came up, well, so somehow this is related to the homotopy groups of top mod O. So this has the information about smoothings of a manifold. And pi 3 of this, it turns out, is the same as pi 3 of a space called top mod PL, which this tells you about PL structures on the manifold. And this is isomorphic to Z mod 2Z. Right, so, well, in fact, PL structures on a top manifold are in bijection with this cohomology group. This is the analog of the fundamental theorem of smoothing theory, but for PL structures. This is because top mod PL is in fact a K Z mod 2Z 3 space. Okay, and so, well, so this is investigated by Antoneda, who proves the statement that I wrote here. And let me just mention one thing which will connect to the next talk, I believe, which is that one ingredient in this argument is work of Milson and Raghunathan about the cohomology of hyperbolic manifolds coming from totally geodesic submanifolds. Okay, so I think we'll hear about that in the afternoon.
Sweet.
Yes?
Here is M your topological manifold?
Yes. Okay, then the second thing I wanted to mention is, so the question that came up before about non-compact. So if M, let's say it's hyperbolic and it's non-compact, but let's say finite volume, then connect them with an exotic sphere always gives you the same smoothing. It never changes the smooth structure. This is an exercise. It's in the exercises. It's a little exercise in smoothing theory. So instead, if you want to know whether these have different smoothings, exotic smoothings, you can consider, well, there's various things you could do. But one is, let's see, you could remove a bi-infinite ray. This is geodesic ray. And then glue it back. So we've seen this kind of construction a few times now. So these can give you exotic smoothings. But the thing I want to mention about this is sometimes, so let me call this like R phi. So sometimes this M R phi has no pinched negatively curved metric. And the obstruction, so Right. So for the smoothings considered by Farrell and Jones, I don't think we know anything like that. We know if you pass to a cover, you can always put a negatively curved metric. I don't know of any obstruction to say that some of these don't emit any negatively curved metric. But in this case, you can use the cusp to get some constraints. So the obstruction is that well, the cusp, which maybe in some case you can arrange for this to be like a flat torus, connects some an exotic sphere. Okay, so you I hope the picture is clear. So you have, this is now our M, and we chose some ray like this. And we changed the smooth structure on that ray. And in particular, on the cusp, the smooth structure changes on the cusp cross sections. And it's a fact that for a negatively curved manifold, the cusp cross sections have to be infranil. But changing the smooth structure in this way gives you something that's not an infranil manifold, and so then you can't have any negatively curved metric, pinch negative curvature. And maybe I'll also just remark that the warping method fails here because the injectivity radius goes to 0 in the cusp. Right? In the warping method, we needed lots of room. Lots of room around the place where we changed the smooth structure. So here you'd need it all along here, but the injectivity radius is going to 0. Okay. There's other things I could mention, but I think I won't say much more. Like, for example, we also know that for like complex hyperbolic manifolds or quaternionic hyperbolic manifolds, you can also get exotic smoothings negatively curved by the same sort of techniques. Okay, any questions about any of this? Yeah.
Is the bundle structure still also amenable, or can we reject the
Say the second part again?
Is the normal bundle or the table bundle or something still, like it admits a structure that you can use a similar technique, or do you need just a new idea?
Yeah, so the smoothing theory computation, which is, I guess, what you're referring to, that use the stably parallelizable, is different. You have to do something different. You need a different idea. And yeah, off the top of my head, I don't remember.
They use AMA to CPN for some of them. And then,
Ah,
and they know that the inertia group of CPN is not trivial.
Yeah. There's something different, but yeah, right. Okay. All right, so in the last little bit, I'd like to just discuss a few things about properties of these exotic negatively curved manifolds. So like I said on the first day, these examples fit in, they're one of a short list of constructions of negatively curved manifolds. And so for that reason, it seems reasonable to try to understand, to study them and understand everything we can about these examples. So, and there's not much that we know, so this won't be very long. The first, to tie it to the second lecture again, they have finitely many totally geodesic hypersurfaces. For any of the k less than 0 metrics. And well, this follows in particular from a recent result of Philippe, Fischer, and Ben Low. I don't know if maybe this was known for these examples before.
Maybe the metric has to be analytic.
Oh, analytic. I see. Well, okay. Well, okay, that's all I have to say about that. So the next thing, well, yeah, I mean, there's various questions, properties of these things to study. One thing is symmetries, finite group actions on these manifolds. And this is, I think, you might think you could understand this in a pretty concrete way because, so for M connects some sigma, well, you haven't, so it's homeomorphic to M. And here you know, well, you know things about finite group actions on M. And so you might hope that you could understand finite group actions on this exotic smoothing as well. So Farrell and Jones observed that these exotic smoothings can exhibit different behavior in terms of finite group actions. Yeah, so let me state the thing like this. Well, so there exists an exotic k less than 0 n compact manifold with an automorphism of the fundamental group such that that's not induced by any diffeomorphism of n. In other words, the homomorphism from diff n to out of pi 1 n is not surjective. So I don't know that. You can, yeah, so this is proved by Farrell and Jones. You can prove something slightly stronger, that the index of the image can be larger than any constant. You could find examples like that. Mauricio and I showed that. but I don't know if you can make it trivial. Yeah. So let me explain the construction. So I think I stated this in my lecture, like the first lecture now, like a week ago, or almost 2 weeks ago. But well, now hopefully, I think we have enough ingredients to actually understand it very concretely. So the construction, you could do this as follows. So you take M, closed, oriented, hyperbolic, stably parallelizable, injectivity radius, large at some point. Sigma homotopy sphere, which does not have order 2. And then you take n to be m connect some sigma. And then you also want, alpha, you could choose alpha to be, so an element about pi 1n, which is, by the way, the same as out pi 1m. They're homeomorphic, and that's the same as the isometry group of m. And we'll choose alpha to be orientation reversing. Okay. And now the claim is, with all of these conditions, this alpha is not induced by any diffeomorphism. So let me just, the argument is short, given everything we know. So there doesn't exist F inducing alpha. So by contradiction, suppose that there is. So that means we have a diffeomorphism like this that induces alpha. And then, well, as in the proof of theorem A, we can compose by, okay, we can use alpha. Okay, let me just write this down, and then I'll say what it means. Let's see. Okay, I'm going to write alpha, but I also need to take the inverse. So this is terrible notation. But this induces the identity on pi 1. And so then, similar to theorem A, this implies that sigma is sigma bar in theta n, which is to say that 2 sigma is 0. But that's contrary to the assumption here. Okay. Questions? Yeah.
Should we expect that the image of the isometry group of the negatively curved metric
The image of has trivial image. You can definitely arrange that there's some isometries. Yeah, I mean, I'll show you why in a second. I mean, you could certainly choose a bumpy negatively curved metric so that the image is trivial, so that the isometries are trivial, but yeah. Other questions? I didn't say exactly what this alpha in quotes is, but I won't unless you ask me. So let me, I mean, it's not hard, but so let me now just state one more thing. Yeah, unfortunately, I erased theorem A, and also the proof of it. But theorem A was something of the form if M connects some sigma was diffeomorphic to M, then they're concordant. Okay, and here what you have, this is an orientation preserving diffeomorphism. And using this, and it's the identity on pi 1. So the procedure is the same as the proof of theorem A. I think it's a good exercise maybe to think through.
So it's not literally theorem A. It's like
It's not literally theorem A. Yeah, maybe the proof of theorem A. It's homotopic to the identity, so then you have the homotopy, you upgrade to a homeomorphism, and then you get concordance of these two. And then stably parallelizable does the rest. Okay. Okay, let me say one more result, which is like a classification in a special case of symmetries of one of these manifolds. Or some of these manifolds. So this is a theorem that Mauricio and I proved. So M, closed hyperbolic. And there's two additional assumptions. So the isometry group of M, I want to assume that this acts freely on M. And also that N, which is the dimension, is 7. So then the first part is that, so if you consider this homomorphism from diff to out of pi 1, okay, what I just told you about from Farrell and Jones is that this doesn't have to be surjective. But it is surjective if you restrict to orientation preserving things. And it's not so hard to see. This splits over G in out pi out plus if and only if sigma is divisible by the order of G in theta n. Yeah. Oh, yeah. So,
Outer homomorphism, what does it mean for preserved orientation?
yeah. Okay. So one way to say this is an outer automorphism induces an automorphism of the homology of the group, and in degree n, I mean that's the same as the homology of the manifold. So in degree n, you want to preserve the fundamental class. But this group is also out of pi 1m, which is like the isometry group. So then you could also define it that way. Sure, let's say M is oriented. It might not be needed, but yeah, let's say that.
So you can't define odd plus for any group. It's not defined for a matched group.
Oh, yeah. So, yeah, I don't know how to define it for an arbitrary group. Yeah. But for pi1 of a manifold, yes. Let me just, before stating the second part, just explain that the backwards implication, which is easier, or easy even. And this will also, Sammy, you'll see the answer to your question about isometries. If you have G, well, G is acting on M by isometries. G is a subgroup out of pi1, which is like isom plus of M. So you at least have that. And then with this divisibility condition, you can construct an action of G on so let's say sigma is G copies of some omega, and then you do an equivariant connect sum like this. And so then this will be an action on M connect sum omega G times, which is M connect sum sigma. Okay, so you can play games like this, yes?
But do you need the whole symmetry group to act freely, or just non-trivial group?
If you know that G does act free, that would be enough. Okay, so that's this direction. And right, so now let me say the second part. If we could say a bit more, so if the order of G is odd, then every G acting on M connect some sigma is isomorphic to this construction. Okay, so it's like classification of finite group actions. G is finite always here on these manifolds. This is somehow the only construction with these assumptions. Desculpe, no falo português. Okay, and so let me just finish here with one question, which would be interesting to know something about. So here, given this classification result, it's reasonable to ask, is every finite group action on one of these exotic manifolds, M connect some sigma, obtained from some G acting on M via some geometric construction? Okay, so this is like an example where the answer is yes. In general, I would guess that the answer is no. Yes?
So, do you know if there is some manifold which exists with properties that you will require in the theorem?
Yeah, that's a good question. So in fact, it follows from work of Misha and Alex Lubatsky that for any finite group you can find a hyperbolic manifold whose isometry group is that group, and it acts freely on the manifold. Maybe this is not what you're asking. I think in addition you can arrange acting freely.
What kind of group you want?
I mean, can you realize isometry groups acting freely?
Yes.
Yeah. Yeah, so there's lots of examples, yeah. Okay, yeah, so like I said, I think the answer to this is probably no, but it's a matter of finding constructions. And as in all of this, somehow this relates to some smoothing theory computations. And well, I think there's more to be understood here. All right, I'll stop there. Thanks.